thank you all for hosting me. Madeline, Joey for organizing. I really appreciate it. Lots of great interactions. You know, it's and it's unusual to do this in your own institution, but we don't know each other well enough, right? And we have a lot in common. We have to work out how we need to talk to each other. It's going to come up a little bit today. My main appointment is in the College of Education, but I consider myself a sociologist with statistics, as mentioned. But I have published in epidemiological journals, and so this is the good conversation to be having. All right, so I did mention, let's see, for the people online, give me just one moment. And you can grab, if you're online, you can use the QR code to grab the PowerPoint if you want that. We'll be circulating the PowerPoint later. It has lots of hyperlinks embedded within. The work that I'm going to be presenting, there is a published paper in Journal of Clinical Epidemiology. There are actually two related to it. That's the first half, and the second half is stuff that is brand new, unpublished. It's a few pages in a grant proposal currently, but we'll take you into it. Excited to talk about it. A little promo ICPSR mini course I'll be doing July 8th through 12th in Ann Arbor, but also online. And then I'll be doing a workshop, Society for Epidemiological Research. It will be the second or third time I've done that. That will be only virtual because I got called for jury duty. And so I might not, so we're going to have to work that out. This is with co-authors Chinwen Lin and Ran Shu, former students who now have appointments basically in epidemiology or biostats, public health. And Shu Sen and Ji-hun are there. My two students, so they helped contribute along the way. Here's a little abstract that was what was used to advertise the talk. So that's in the slides. So a little overview. We'll talk about why sensitivity analysis. Then we'll talk about the robustness of inference to replacement. How much of your data would you have to change your mind? We'll do that for fragility and for a 2x2 table, as well as an extension to logistic regression. I have some questions for you. So I'll put those out there when we get there. And then that's kind of the first half. And then the second half will extend the thinking about robustness of inference to replacement to hazard models discrete time, which are basically logistic regressions. So that's pretty easy. And then the new work that's really unpublished is about continuous time hazard models via Cox regressions. I was doing one last little computation this morning on this, and we have some different techniques for this. We got into this because I did a workshop or a course about a year ago, and there was someone in medicine who said, well, all we're using is hazard functions these days. What do you got? And we got to thinking, and so that's what you'll see here. And then a little conclusion. All right, so motivation, why sensitivity analysis? In our world, we're going to try to say X causes Y. We're going to try to make a causal statement. Even if you think you're only describing people, if you're pragmatic, they're going to try to want to make something policy. They want to take some action. So we're going to take some action if we think X causes Y. And that's what's called policy sociology, putting on my sociology hat. But it's just policy. When we do that, we engage the public or publics, lots of different groups of people. And you could think of this for any of the actions. You're thinking if pesticides could cause dementia, then maybe we would change policy regarding pesticides and what could be used, what could wash away, right? We were going to call for some action. And that means we're going to call for some resources, which I represented with a $sign. Well, somebody might not like that. Some farmers trying to get the most per acre might not like what you're doing, or somebody else. So they'll say, you cannot prove X causes Y. Therefore, we shouldn't take the action. We want our resources to be where they are. And this isn't somebody who just wants $1 million. This is somebody who thinks the resources should be spent in a better place. They have something else that they think would be very important, and they don't want to divert into the thing you think is important. Well, what are we going to do about that? So the pragmatist in me, and that's the conversation I've been having all day, says, I don't have to prove it. I have to ask, is there enough evidence to act? And that's a different question. So now I'm representing that with a dashed line. And that dashed line is enough to link to action. So I want to try and get out of the business of trying to prove something just enough evidence to warrant the reallocation of resources. Put the other way, if there's enough evidence to act and you don't take action, that's not a good thing. That's wrong. There was something out there that could have worked and you didn't pay attention to it. The best example of this, the first example of sensitivity analysis, has to do with the effect of smoking on lung cancer. And so some people were finding a relationship between smoking and lung cancer. Other people said you cannot prove that smoking causes lung cancer. And in particular, R.A. Fisher, who invented half the statistics you're aware of, was one of the ones arguing you cannot prove that smoking causes lung cancer. This is Fisher publishing in a journal. It's an obscure journal. It's called Nature. He also published in Science, a very similar editorial type piece. And he says both characteristics, smoking and lung cancer, might be largely influenced by a common cause. And Fisher, for all his horrible aspects, he's sort of eugenicist, but he's brilliant. The guy is smart. He will have your head spinning. Oh, yeah, he's wrong. Oh, my God, he's right. And along comes Jerome Cornfield, who's, I like to think, kind of more like me, just trying to get it right. Let's just, come on, And Cornfield got together a bunch of other people. They wrote a very prominent report, and they reviewed the evidence relating smoking to lung cancer. And this report is about a dialogue with the public. And there's an appendix in the report. It's really the beginning of sensitivity analysis. It's not written beautifully. So Rosenbaum later on kind of wrote it. And he said, Cornfield found that such an unobserved characteristic, Fisher's characteristic, would need to be a near perfect predictor of lung cancer and about 9 times more common among smokers than among non-smokers. The sensitivity analysis does not rule out the possibility that such a characteristic might exist, but does clarify what a scientist must logically be prepared to assert in order to defend such a claim. Note that there's a lot going on in that statement. First is what the omitted variable would have to look like. Those are mind-boggling associations. By the way, they did find Fisher's gene in about 2014. It explained about 10% of the relationship between smoking and lung cancer. It's still smoking has a strong effect on lung cancer. The other thing going on here is look what's going on. They're not trying to prove it. They're not saying we prove smoking causes lung cancer. They're saying this is what you must assert. They're entering a dialogue. They're initiating a dialogue about the finding, and that dialogue is what informs policy and practice. That's what sensitivity analysis is about. And that's actually kind of a misunderstanding. People will say, I can't use, Ken, your techniques won't show if a model's good or not. I mean, you're right, it doesn't. And what it does is allow us to talk about how good it is, and that brings more people into the conversation. That's the pragmatic sociologist to me. All right. So what Cornfield does is like the first huge step in sensitivity analysis, and the most important and the biggest step. But we could do a little bit more. It's expressed in terms of an omitted variable. There could be other sources of bias. It requires thinking about 2 odds ratios embedded in Rosenbaum's statement. That's a little rough. Relationship to the predictor, smoking, the relationship to the outcome. I have to balance both in my head. Vanderweel's E-value assumes that the 2 are equal. That's one of the approaches he does. So he does a little bit more than that. And I've done work similar to this. So it's a solid line of work. But what I want to bring out today is to get you thinking in terms of people instead of variables. So we're going to talk about what % of the people would have to be replaced with cases for which there was no effect to change the inference. And that, I think, can resonate with practitioners, different stakeholders, policymakers. I mean, how many policymakers can balance the 2 odds ratios in their heads and the implications of that? On the other hand, I think you could tell a policymaker, well, if a third of the people in that study shouldn't have been there, the inference would change. I think they can get their minds around that. The other thing is, and we'll see this, that when we talk about counts of people or percentages, those can be accumulated or compared across studies, which is a really nice aspect. Imagine saying this study had these 2 odds ratios to change the inference, that had 2 other odds ratios. That's tough to compare. But what if I said 30% here, 50% there? What if I combined studies and said across 2 studies, 100 people would have to be different? Those are much more tangible terms. Okay, so we'll take you into robustness of inference with replacement, RIR, for logistic regression. So let's ask how much and in what way must you replace your data to change your inference? And this links to a broader robustness of inference to replacement thinking that has continuous outcomes and many other applications. We're going to replace cases with zero effect cases. What's a zero effect cases? In a logistic regression, it might be one in which the probability of success or a positive outcome is independent of the predictor. We'll see that. And this is going to be related to switching some cases from treatment success to treatment failure. I'll give you graphics. It's just a little overview of where we're going. It's based on a couple papers that did appear in the journal Clinical Epidemiology. All right, so I've got this example worked up. We're going to work with it. We could do other examples as well. This was an example early in COVID. Donald Trump was saying that HCQ, which you all anyway, HCQ seems to have an effect, a positive effect on people with COVID. This, when he said it, given the timing of when he said it, the study here cited is probably the one he was referring to. And sure enough, if you do a chi-square test on this table where we have HCQ versus conventional treatment and improved versus exacerbated or unchanged, if we look at that 2x2 table and we do a chi-square test on that, the p-value would be 0.03. So statistically significant, seems to have an effect. Let's figure out how robust that finding is. What I've done is I've taken the numbers in that table and I've just reproduced them right here. And then I've reproduced them with little smiley faces. If there's 14 in this cell, then there's 14 little smiley faces here. Part of what that's supposed to give you the feeling of is that within a given cell, in categorical or qualitative, sometimes called qualitative data analysis, in the sense that it's just groups, within a given cell, people are interchangeable. You can't tell if somebody got the treatment and improved, you can't tell the difference between that person and any other person in that cell. They're all the same. With a continuous outcome, that wouldn't be the case. But with okay, so all right, so I've reproduced it here. And you can see that in general, about 2/3 of the people get better, whether, independent, if you will, of conventional treatment or HCQ. The blue means they got better, the red means that they did. That's how we've represented. So let's think about what it would take to change your mind. There's your 2/3. There we go. If we replace 3 of the treatment improved with people drawn from this distribution where about 2 out of 3 get better anyways, we would see that when we replace them, 2 of them would be replaced with interchangeable parts. You couldn't tell the difference. But 1 became a failure, a worse outcome. And that 1 essentially constitutes a switch from treatment improved to treatment failure. If you now did a chi-square test on this new data with the 1 switch, the p-value would be bigger than 0.05. So now we can say that to change your inference, 1 switch from treatment improved to treatment failure would be required, and that's called fragility. That switch is called fragility. Or to create that 1 switch, we would replace 3 cases, 2 of which would be, I need to be careful about cases. We would replace 3 people. I use cases differently than you do. We'd replace 3 people who had got the treatment and improved. It turns out 2 of them would have improved anyways, and then therefore 1 would have failed, and that would have caused a switch. So the switch is fragility. The replacement is robustness of inference to replacement. The reason why the robustness of inference to replacement is important is it doesn't quite show up in this example, but if getting worse is really rare, such as was the case with COVID early on, someone getting infected, it was 1 in 1,000, right? People weren't, 1,000, whatever. Maybe it was 1 in 100, but it wasn't like half the people were getting infected in a given day. So when it's a really rare outcome, maybe a switch, maybe it would take 100 cases to create 1 switch. Maybe it would take 1,000 cases to create 1 switch, 1,000 replacements to recreate 1 switch. And so the switches are important, but what forces it is the replacement of the data. All right, good. And this is one of the critiques of fragility, is that it didn't account for the prevalence of success or failure overall, and robustness of inference to replacement does. So we like to report both. What we do in practice, for what it's worth, is we first figure out the switch, how many switches are needed to change your chi-square test or whatever test you're going to use. And then we figure out, well, to generate those switches, you'd have to replace 3 cases. So we actually, the process is reversed in calculation, but the thinking can go either way. You can try it. Get out your phone. Part of this is about you all doing this. So then you know how to use it. So if you, okay, for like me, my kids, I had to tell me, Dad, it's a QR code. You hold your camera up and then you'll be able to get to the website. So, all right. So if you put on the QR code, you can give it a shot, and you're going to tell it, you're going to get to our little app, and you're going to put in a dichotomous outcome, 2x2 table, generalized robustness of inference replacement, and then you'll put in these 4 values to represent the 2x2 table, and you'll click run, and you'll get either, you need to replace 2 or 3 cases. I'll explain that in just a minute. Shusen and Jihun can tell you all about whether it's 2 or 3. They spend hours and hours sweating it. So give that a try. Give me a thumbs up if you got it to work.
You have to select like the non-model, right?
So we might have a little version control problem. Okay. So that, no, all right. So I'll tell you what I'll do. I'll do it live. So we just upgraded, and I think my slide maybe had the slightly, so this should be what you got. No.
Here's a menu option, linear model, work.
I think I got the wrong QR code in there. Okay. Can you just, sorry about that. Can you just Google confound it? It would still work. It'll work. What you have will work. This just looks prettier. Oh, shoot. All right. I gotta update that QR code. Maybe. Give me a second. It's not, so how can I, okay. I know what I'll do. I'll just be patient here. Oh, did you get to the website?
Yeah.
Oh, I did do it right. Okay, got it. We'll go to the website, and then yeah, and then you can just start confounding. There's one extra step. Sorry about that. Here you go. Now, if you click on start confounding, you should see what I saw. Okay. I should have shown you that. All right, good. So now you're going to click dichotomous, 2x2 table. We're going to do generalized. We only have one choice here, but eventually there might be other things. And you'll put in the values in this cell. You can go with anything you want. If you want to reproduce what's on the slides, you would go here and put in 14, 17, 6, and 26. And then you should get this statement. It's either going to say replace 2 or 3, and it does say cases, but it's people. With null hypothesis cases, the RIR is 2, and the fragility is 1, the switch is 1. So give me a thumbs up if you got that working. Okay, good. All right. So one of the reasons, and I think, I can't remember who I was talking with about, maybe it's Matt, this is the dissemination mechanism. You know, I hope you'll use it. The idea is you could do this at a conference. You could do this on a paper, you know, pretty easily. For those of you who, and then this is like an entry point. And then once you've run something, you can have it generate R code that would run the same thing. And you can copy that R code and run it. Now with the 2x2, at the moment, it says coming soon. And Again, we'll point to Jihun and Shusen. It really is coming soon. We've got all this working in Stata now. Now it's a question of releasing the new Stata version. It'll be out in like 2 weeks. That's what I would hope. And so this would generate Stata code for you that would allow you to run this analysis. So if you do it at a conference, just don't be obnoxious about it. Right, but somebody will argue, oh, that was you should have controlled for this, or it could be that. You can come in and say 100 of the people would have to change the inference, or maybe 2, and that can inform the conversation. Good. So now we go back here.
So according to this scenario here, the robustness of replacement, that number WI behind the QR code, is that?
It's 2, or it probably, well, it's going to depend. It's 2 right here. You might have gotten a value of 3. The 3 is more accurate. It really is a rounding issue that we had to struggle with in there. Yeah, so 3 is more accurate.
So it's not like you count a new transfer table cell that look like only one of the treated got from success to failure.
Yeah, so one switch, that's the fragility. You can see the one switch from success in the treatment, from success to failure. That's the one switch. But to force that one switch, you'd need to replace 3 people. Yes.
Can you do the opposite and force a switch on the controls, or does it always only work in 2?
Stay tuned.
Okay.
Yes, if you're running the R code. No in the app at the moment. But I'll have a slide on that. It's a good thing to be thinking about. All right, good. So we ran that. You can do the same thing, which I think I won't take the time on a logistic regression. So there was a fair amount of math behind this, but if you input an estimated effect in terms of a log odds ratio, a standard error, and then these other values, total number of cases, number of covariates, and number of cases in the treatment condition. That's what those values are. If you enter all those, it figures out the implied 2x2 table, and from there it does its work. So you can run this off a logistic regression, which allows you to take into account covariates. Now, when it does that, you should know that this implied 2x2 table might not really exist. It's implied by the it's implied by the estimate and the standard error. And so if you looked at the descriptives, that wouldn't really exist, but it's sort of, like I said, implied. And I want to get rid of that. Sorry about that. Okay, good. So you can do a logistic regression, which will come up when we want to do hazard functions. All right, this is just another example of a logistic regression where it did a 2x2 table and moved things around. There is a Stata paper about this. The Stata paper does not have the logistic regression in it, but that is coming. And there is a recent JOS paper. These are both hyperlinked in the PowerPoint, so you could click on stuff. The JOS paper is brand new. Journal's open source software. So we've been writing about these things. If you want to be running new versions of things, here's a little bit of code so you could run it in R, which I will go past. And if you wanted to run the logistic version in Stata right now, you could click on this link and it would take you to some files. You have to put them in your personal folder and then you could run it. That's just a little clumsy thing that'll be fixed in 2 weeks. All right. First, which cases to use for replacement? The reviewers pushed us on this. I pulled them from here. I pulled the rate of success from the overall. You might think that the control would actually be a better place to pull the replacement cases, replacement people from. That would actually produce a more conservative, a lower robustness of inference replacement, assuming you found in your data evidence of a positive effect. So that's worth thinking about, and that's an option in the software. Matt's question. You could move from conventional got worse to conventional improved, or you could move from treatment improved to treatment got worse. Could go either way, and that's an option in the software. You could even move from here, from treatment worse to conventional worse. And that would be evidence of a compliance issue. So, oh, the person, you think they were treatment and got worse. Actually, they were control and got worse because they didn't take what they were supposed to take. So how many of those would there have to be to change your mind? You could do that calculation. It's all the same kind of game. Yes.
So I was just trying to post that back when I did my thesis, we did random brute force misclassifications. We just knew 25% of people all moved randomly somewhere else. So all of your methods are all making assumptions. It's this way, it's that way, it's kind of like the rate of total. Do you do something with random? Like is there the whole 2x2 table, 20, like a certain percent of random is classified or changed the answer?
So that's interesting. Well, I think what you did was very sophisticated. And, yeah, it's brute force. And one of the things, I think it's fine what you did. And it actually lets me talk about something. So I would rather, I want a targeted, well-informed conversation. And what you did is accurate, but it's a harder conversation to have, I think, because 25% in this example, but 29%, you probably came up with a distribution of percent to move around to change your inference. It wasn't always one number, right? Yeah. But here we're going to make a very controlled assumption that the replacement rate is defined by exactly the percentage of success here, or here. And then we're going to replace a very specific number. So I think this makes it for better conversation. I think more people can understand this. What you were saying, it would be very similar, so that's what I would say.
It's more worried about noise and imprecision.
It is. It is. And in some sense, what you did is more authentic in terms of what would one really do. Well, they would randomly toss stuff around. But ours, I think, is a hypothetical, idealized conversation. And there's a guy, Ben Baer, who published in PNAS, who did something closer to what you did. One of the things you can do, now that we've got this RIR tool, we don't have to use statistical significance as a cutoff. We could push our fragility or our RIR as far as we want. That's what we've done on the x-axis here. And look at the difference in probability between treatment and control and how that changes with each new switch or each new replacement. So if you went over here and replaced 16 cases to produce 5 switches, 16 people to produce 5 switches, then if this was your cutoff, a probability of the outcome difference 0.1, if this was your cutoff, we know what it would take to produce it. This is all by way of saying we can do statistical significance, we can do clinical significance, we can do any cutoff you want. We'll give you the chart, you pick. You pick what your threshold is. A little comment here that you already have a way you think of informing the robustness of an inference. It's the p-value. 1 star, 2 star, 3 stars. One of the problems with p-values, there are a couple problems. But if we were just going to use 0.05 as our standard cutoff, then when you see 2 stars, that would probably translate to about replacing about 25% of the data. When you see 3 stars, that would translate to about 40%. The problem is if something's 80%, you can't see it beyond the 3 stars. And even if you could, what if you put 5 stars? Who here can understand 1 in 100,000 versus 1 in 75,000 versus 1 in 10,000? Is that intuitive? And that's hard to get your mind around. If I said you'd have to replace 85% of your data versus 40% of your data to change your inference, that's much more intuitive. So there's a lot of information lost when you use your p-values. And that information is actually critical to characterizing the most robust inferences. Another thing we can do is we can do a cumulative meta-analysis. That technique has existed. And this has to do with antihypertension treatments, medication, starting in the 60s. And the little black dot tells you the cumulative estimated effect. The blue dot tells you what would have been just statistically significant. And in the boxes tells you the RIR, the cumulative RIR, the robustness of inference to replacement. So as you go along, you see that the cumulative estimate kind of settles on a 0.02 effect. But the RIR keeps going up so that by the end you would have to have replaced about 5,000 people to change your inference. Yeah.
Does the graph look similar if you're just focusing on removing individual studies from that analysis rather than cases? Can you do that with this, or is that a different analysis?
Okay.
So if you got a meta-analysis of 20 studies, how many negative studies would I need for this?
Ah, well, that's interesting. So it depends how you do the meta-analysis. That's interesting. Okay, so if you do the meta-analysis, the way I learned to do it is sort of with a multi-level framework. So you have a bunch of observation points within each study, and then you combine them all. So when it does that, it is weighting each study by its sample size, more or less, or its standard error. We'll know its standard error. So then you could do this, but you would have to recognize that when you removed a study, you'd have to recognize its sample size. There would be an implied sample size. If I removed a study with a very large standard error, that would not change things much. If I removed a study with a very small standard error, it would change things a lot. So it kind of pushed things back to a function of sample size. All right, this is brand new as of yesterday. It only will work for education data. And I'll just do a fixed demo, like, I'm not going to go live, but if you clicked on this, you would get to this app, and we can, this is Spiro Maroulis and a student Dowland idea. We can do the RIR for a whole bunch of studies and look at the distribution of it. So we can know where your study would be relative to other similar studies. So you can click on any of these things. There's a large education database with all these studies and their results. They tap that database, did a lot of work to convert to effect sizes. You can make all these choices about what kind of outcome you want to look at, et cetera. And then you can get a distribution of RIR values. And you can even locate your own study in that distribution. So then you could say, well, our study is more robust than 2/3 of the other ones, or 1/3, or 5%. You'd know where you stood. I won't go into it, but if you want, try it. But that's only for education outcomes because it's only been cranked up for the education data. I will say, though, if somebody here wanted to do something similar for epidemiological outcomes, if you can find the studies, I think we have the technology. It's leveraging Hedges G for effect sizes, which is a pretty nice way to do it across studies. Here are some alternatives, which I won't go into too much. That's what we covered. Here are my questions for you. What's the best form of input, and what form of output? So some people have told me that in medicine, they would rather input a confidence interval rather than a 2x2 table. We could work with a confidence interval, so we're going to work on that. 2x2 table logistic, are any of you doing probits or fancier things? What about difference in probability? So interested in that. And then I've been told that this format of the table is very jarring for epidemiology, to put treatment and positive outcome in the lower right-hand corner. And I just want to know if that's true. Is that like messing you up? Yeah.
And the confidence level, I guess the reason I maybe want to use that instead of 2x2 table is that if I already adjusted for the bounders, right? So I have my final model adjusting for separate bounders. To figure out the 2x2 table kind of works on versus when you get a little bit better refinement.
Yeah, the confidence interval, that's true. So that's good. So the confidence interval could be applied to just the unadjusted effect, in which case 2x2 or confidence interval. Confidence interval could be applied to the logistic regression. We're asking you right now to put in your estimate and your standard error, but if you know the confidence interval, we can figure out the estimate and the standard error and back and forth. So that's actually a good point, that the confidence interval you'd have to clarify, is this an adjusted confidence interval or an unadjusted confidence interval? Let me make a little note of that. If you don't mind, yeah, I'll just make a little note, because that's something we want to keep track of. Okay, good. And anything else you think about this would be interested. This is our little interlude, and then I'm going to switch to. Oh, yeah, okay.
Quick question. So I presume the direct relationship between the width of the confidence interval and the fragility number, like if you took confidence intervals and the fragility number, I mean, I think before now we would just look at confidence intervals and it's wide, well, it's, you know, it's fragile, but do you think there's how directly correlated do you think those two things are?
It's a 5-minute answer, but I can,
Not as
let me do it in 30 seconds.
Yeah.
All right, I'll give you a 30-second answer. When we do robustness of inference replacement, not for logistic, when we do it for continuous outcome, we do it as 1 minus the threshold value over the estimated value. It's basically the percent at which the estimated value exceeds the threshold. 30% of the estimate is above the threshold. Okay, that's how we would do it. To do that, I'm using a threshold and an estimate. The threshold is 2 times the standard error. That's the width of your confidence interval. Wow, that's half the width of your confidence interval. The estimate is the center of your confidence interval. So I'm using the same 2 pieces of information used to define the confidence interval, but I'm converting it into replacement of cases. Replacement. All right, and I could show that in slides, but that's. And then I would say to you, for those who love confidence intervals, what does close to 0 mean? Think about it. The wider the interval, the closer it looks to 0. If 0's here, and here's the edge of my interval, that is further from 0 than that. But the bottom didn't change. What changed was the width. And the width is basically the threshold for making an inference. Yeah.
So this here assumes like you can estimate the prevalence from this table, right? Basically, the prevalence of the, because if this is a case control study instead of a randomized trial or a cohort study, you wouldn't know that.
Yeah, so that's interesting. In one version of the software, you could put in, or we talked about putting in your own prevalence value. Just, I know the prevalence is 20%. And then you could proceed that way. Yeah, there's nothing really stopping you from doing that. Yeah.
Like, so I had another question with the cumulative meta.
Okay.
Because I first thought it's counterintuitive, like you need to replace more cases when the effect size is smaller. And then I realized this must be because the prevalence is changing based on the cumulative studies, like it's becoming rare.
But you're accumulating information across the studies. So the first study, let's say you only had, well, it says in the bottom here, the first study was based on 87 people. By the time you're at the end, it's based on 37,000 people have accumulated. So then it'd be 5,000 out of 37,000. What about 1/7? Yeah.
But the prevalence is based on the.
It would be. And so that's interesting to think how the prevalence would change and therefore the replacement would change. We didn't even think about that. I think it's an interesting thing to think about. All right, good. Well, that was part 1. You can stretch a little, catch your breath, and I'll do a little bit on hazard functions. First thing is for Kaplan-Meier discrete time hazard. If you don't know hazard functions, you'll see a graph. You'll see a graph, okay? But I'm just going to say this, for discrete time, it's a logistic regression. You just have a bunch of dummy variables indicating which interval. That's easy. I just showed you logistic regression. So we'll go past that. And this is the continuous time, and we'll have a little fun with this. So this is what the data look like in a hazard model. You have these control people and these treatment people. This is like time until they got better, or time until they got worse, or whatever it happens to be. The timeline is time, and the line is time. And then this estimate is the average difference in risk ratios over time. I'm not going to go too much into that. Okay. But the key is that it's based on these relative positions. And that's the average difference in hazard. What if we removed one control case? What would the estimate be? Well, the estimate would now be 2.39 instead of 2.49. Removing a control case changes the estimate. What if we remove the first two control cases? Now the estimate's 2.249. Oh, I'm getting the hang of how to change the estimate. What if we have a censored case? Oh, it never happened, right? Well, then it becomes 2.39 again. What if we move a case to the median of the treatment? Now that's an interesting thing. You had this control situation that had a relapse fairly early. But what if that's a mismeasurement? Or what if it really should have done better? Now that's a pretty powerful jump. And now the estimate is 1.39. Wow. Moving one control example to the median of the treatment really pushed things. This is how we're going to think about things. How would your data, how would the rank orders have to have changed? And how much to change your inference? We could move the third control person to the median, and it's the same thing. It's the same result. It doesn't matter whether you move the first one or the third one. What matters is which group they came from, because the ranks, the Cox regression is leveraging off the ranks. So that's pretty interesting, and that's going to become important. That means that if we move this person from here to here, it's the same thing as moving this person from here to here in terms of the ultimate implications of the estimate. It only matters which group it came from and which group it moved to. Within a group, it doesn't matter which person you moved. So now we could say how many moves from the control group to either the maximum value or the median value. We can make a number of moves and look at the corresponding change in coefficient. The coefficient started off at negative 2.5. If we want to make it 0, we could move it 2 people and move them to the median. If we want to make the effect positive, we could move 5 people and move them to the median. Now we know what we need to do to change things. And that gives us an interesting little tool called the Macaroni Index, MCRNI, mean change in rank to nullify the inference. You have the initial ranks, the sum of the initial ranks in the treatment, minus some threshold that you're going to use to make an inference divided by the number of people in the treatment. And there's the macaroni. So here's how it works. The threshold, you might use a Mann-Whitney-Wilcoxon test to test the difference between the ranks. It's a non-parametric test. It's a test used to test the difference between the ranks. A little bit of math here. You pop the numbers in and you find out that if the ranks were 38, it would be just statistically significant if the ranks in the highest group were 38. And now we know that the ranks in the highest group, the sum of the ranks was 39. If you summed up the ranks in the highest group, for the example I gave, it was 39. So you would have to change a total of 1 rank for 5 people, an average of 0.2 ranks per person in the highest group to change the inference. Now you know what it would take to change your mind if you're using statistical significance and a non-parametric test to test them. So it's how much would you have to move the people around? You can do a little normal approximation. It turns out the normal approximation for a Mann-Whitney test is really good. You don't have to work through all this. It's in the slides. That would have told you the threshold value is 37, basically almost the same as we had before. So that's nice. And you could even use this, the normal approximation for ranks, the sum of ranks, to get a z-score. And if you did that on the original sum of ranks, this is the ranks in the highest group, the sum of them, and this is the mean and standard deviation according to the normal approximation. You get a z-score of minus 2.402. In the Cox regression is minus 2.49 as done by R. That's almost identical. The advantage of that is you give me a z-score, I can do all kinds of sensitivity analyses of that. That's really easy to work with. That's how I work with continuous outcomes. Everything is, I could do a whole lot. So I just want to show you that. I know it's a little, you don't have to go through all the math, but the fact that these two are so close, yeah, you could do the Cox regression, or you could just create a little z-score and we'd be in business. That's really important. And I want to note here that the standard deviation for the sum of ranks is based on only the number of people in each group. It doesn't, so that means I can switch them around all I want. The standard deviation doesn't change, standard error doesn't change. All right, that's a little geeky. I'll note here that we have something called the minimum score to nullify. If you make these two moves, yes, it's an equal change in ranks, but one of them creates a bigger change in scores than the other. So we could talk about the smallest score change to change the rank. We can also do partial derivatives. All right, so questions for you, which would be most useful? This is brand new. So what I'm showing you is the calculations are days, hours, days, and months old. But you know, if thinking about switching around the people makes sense and what would really resonate with you, if you're an expert in hazard models, you know more than I do. But I'll pause there and get your thoughts. And I'll see if there's anything in chat. The chat was firing up before. Oh. Okay. Nothing going on with that.
I think the problem is we don't think about ranks on when we're doing our, I mean, we probably should, but I don't think, I think we've lost sight of actually, this is all ranked and you just look at our curves and you're going to have a function and run with it. So I think it's interesting because it's making you really think about the fundamentals of the data.
So that's what happened to me. So when this guy brought up that, hey, we all use hazard functions, I went back to some old books I had and started looking them up, and I realized, and I started thinking, it's a function of the ranks. I can't believe it. And then I started playing around, and you see here, it really is a function of the ranks, because changing the hazard function, if I remove this case, is the same as if I remove this case. It's indifferent to which one you pull from group one. And so that was striking to me. And as soon as I saw ranks, these non-parametric things, which are really easy to calculate, are how you deal with ranks. So, all right, it's a little into the methodological mind, but I think I want to put this back on the tape. This is I mean, I didn't make this. The people knew how ranks were driving this, but yeah, I think we might have lost sight of that.
I think a lot of that lost follow. Yes, it's, you're kind of taking the data after we followed everybody that we could, right? Those losses are gone. Every time you took a person out, I thought about, well, that could have been somebody who lost a follow-up.
Excellent
So
attrition.
I'm trying to think of how we can use it to maybe better assess how much I lost a follow-up in certain months.
So instead of, I did it as censoring. What if it was censored or removed? But it could be just due to attrition.
Right.
Right? Yeah. So I think that's good. We haven't, I like that. It's definitely how we could use some of this. All right, well, coming to an application near you eventually. I think that's probably, I think I want to do the slide if I can, and that's probably be a good place to wrap up. If we want to look at a change in policy or practice, there's a counterfactual for the people who got the treatment. I think you all know that. And there are true effects. As soon as you say that, though, as soon as you say there are true effects and there's a counterfactual, that means that our business is approximating that counterfactual. That's what we're doing. It opens the path, it opens the role for the researcher, because you're never going to get to see the counterfactual. The reason why I bring that up is the qualitative people will tell you all the time, oh, the researcher is the instrument, the researcher is part of the process. As soon as you say counterfactual, it's true for the quantitative person too. You might like to use regression discontinuity. I might like to control for lagged outcomes. There are a million decisions being made. And so we weigh in on that. And with that, you won't have the last word. You're going to have to talk about it. You get to say something, but there should be a conversation. And that's where the sensitivity analysis should come in. So this is from another paper, but I thought I'd throw it in there. I mentioned as somebody pretest, the importance of pretests earlier today. If you click on that link, you'll see it written up. Good. That's a good place to stop.